Hello, and welcome to our Group Design Project presentation, Robotic Device Solutions for Volcanic Exploration. This project spans the final 2 years of the Engineering Design degree course, the first of which is spent individually researching and modelling various aspects of the project's subsystems. The outcomes of this are then taken forward in the second year of the project, where the group comes together to produce a final single output, which in our case is a prototype device.
We will start by giving an overview of the project and the initial concept development process, before going into more detail about the final device's design and testing. The conclusions we've reached and our recommendations for future work will also be covered at the end of the presentation.
Volcan de Fuego is an active stratovolcano in Guatemala, which has been the subject of extensive research by the Bristol Flight Laboratory team at the University of Bristol. They have used UAVs to gather footage of the volcano and data about its plumes and ash clouds. The purpose of our project was to further their research by designing and building a device capable of exploring the surface of the volcano's crater and collecting environmental data, something that, as yet, the Flight Lab hasn't done.
As you can see from the footage, Fuego is, to put it mildly, incredibly inhospitable. There are regular eruptions, expelling projectiles varying from the size of pebbles to small cars, acidic gases, potentially very high temperatures, and an unpredictable, constantly changing topography. Designing something able to operate there was always going to be challenging.
The top-level requirements of the project were identified as follows. The device must be providing environmental data such as temperature, humidity, and pressure. It should be capable of exploring the crater by driving for more than 10 minutes and capable of transmitting imagery to the user as well as acquiring a sample from the crater. We were also informed that if we produced a deployable device by the 23rd of March, it will be taken with the Flight Lab team on their upcoming trip to Guatemala and deployed in Fugo's crater.
Our collective decision based on the individual research projects was that developing a device that fulfilled the full extent of the requirements would be unfeasible in this timeframe. Given the unique opportunity and invaluable insights that would be gained from actually deploying a device, we decided to instead focus our time on producing a device that could be delivered on time and would fulfill the highest priority requirements. To inform the decision as to which requirements would be focused on, Quality Function Deployment Analysis, QFD, was performed. We compared the relative importance of requirements, the technology readiness levels, and the interdependencies between each, and decided to eliminate the sampling subsystem and device retrieval. Due to the complexity of the system and the number of necessary subsystems, we followed a Paul-Bates design process model for concept generation. We used a morphological chart to generate a range of full system concepts, each based on a general theme, for example, easiest to manufacture or most suitable based on Year 4 research. To select the most effective concepts, multi-criteria design analysis, MCDA, was used twice with increasing degrees of resolution.
The top 3 concepts are shown here. These were taken forward, and the relative merits of each were discussed with respect to the project's functional requirements. The chosen concept is a combination of the outer 2 concepts. The final design consists of a 6-wheeled device with a monolithic chassis, onboard battery storage and manual control system, all encased by an external composite shell.
As might be expected on a project such as this, the final device doesn't look particularly similar to the final concept sketch that we just presented. However, the core elements remain largely unchanged, while the form itself developed to meet our needs. A cornerstone of our process for the detailed design of the device was rapid prototyping, which we used to quickly interact with components as they were designed and make changes as necessary. The device's electronic systems were designed and implemented in close collaboration with members at the Flight Lab, who have a wealth of experience in implementing similar systems on drones. It was also vital to keep a close eye on the interaction between all the physical components and subsystems, so an up-to-date CAD representation of our latest designs was essential throughout.
The locomotion system for the concept device, as mentioned previously, was a 6-wheel configuration. To carry out the detailed design of the subsystem, research of existing 6-wheel devices was carried out. Following this research, a multi-stage design approach was used for the different subsystem components. The first main design decision was to use 6 independent drive motors instead of 2. This eliminated the need for power transmission from one motor to 3 wheels, as 6-wheel drive was deemed essential. Using independent motors reduced the mass and the cost of the subsystem and increased the system redundancy, as if one motor were to fail, the device would continue to move around effectively. Wheels were then selected from an RC car supplier, selecting a high-tack rubber compound with deep tread and maximising the wheel diameter given the maximum device size envelope. Using the device's maximum allowable mass and the wheel diameter, the required torque and speed of the drive motors was calculated and suitable motors purchased. A motor housing and the suspension pivot was then designed. It aimed to maximise the distance from the wheels to the pivot point so that the angle of the wheel would not change significantly when the wheel was deflected. Finally, the suspension system was designed. 4 different prototypes were produced using torsion, compression and extension springs. Following testing of these prototypes, the extension spring system was chosen due to its simplicity, low mass, low cost, and the ability to easily change the spring stiffness. The final design of the locomotion system is shown here, with an exploded view highlighting the components required. Testing was carried out following a full design prototype. These included the maximum gradient, maximum step, speed, and the device's ability to move over a range of terrains. The testing proved very successful, with the locomotion system achieving all of the design requirements. For the final device to be taken on mission, the parts that were made from additive manufacturing were made using selective layer sintering of nylon to increase its strength and durability.
The electronic system of the device consists of sensing, control, and communication, along with power considerations. The sensors on board act as a guide for navigating the device and offering live environmental data. The control system receives feedback from the sensors on board and the user at the ground station to perform necessary tasks on the device. The motivation of selecting the hardware and software was based on fulfilling the client specifications, reducing the weight of the hardware where possible, ensuring ease of integration of different electronics, and respecting the budget constraints. Where possible, electronics which the flight lab is familiar with were used to ensure the ease of future modification. The selected hardware was then integrated with other electronics and subsystems of the device. This integrated system was then tested to ensure fulfillment of the original brief. This slide presents an exploded view of all electronics and their placement on the chassis. The device uses a thermocouple and an environmental sensor to measure the air and ground temperature, along with pressure and humidity in the air. The position of this device is achieved using sensor fusion of GPS and IMU. Live FPV visual is achieved from the DJI FPV system and viewed using the DJI goggles. The video is stored on board at 1080p and can be recorded on the goggles at 720p. The benefit of using the DJI FPV kit is that it offers not just video communication, but also device control, as it comes equipped with a controller offering a range of 4 kilometers. For controlling the device, an F405 wing flight controller was chosen. A flight controller was chosen as it's a simple smart processor capable of assisting integration of electronic components without the need for intensive coding. This leads to ease of implementation. Ardu Rover, an open source firmware, was installed in the flight controller to support its control and integration with the ground station. Lithium polymer batteries were chosen, offering the power for a 10-minute drive and 1-hour environmental sensing data. The flight controller communicates with the ground station mission planner using a 900 MHz RFD, offering a range of 10 kilometers. Mission planner is used to wirelessly view the status of the rover, such as position, orientation, and battery life. The user can also switch between manual and autonomous mode using mission planner by setting up a path plan using waypoints. Although since the rover is not equipped with obstacle avoidance technology, it is recommended to monitor the rover's motion using FPV to avoid collision. The drive of the rover is controlled using the DJI FPV kit. The air unit uses multi-antenna technology for receiving commands from the controller and transmitting video feed. This ensures broader signal coverage for reliable control and transmission. The downside of the system is that its maximum operating range is 4 kilometers. Therefore, the user needs to be located at active angle and can't use it from the observatory. The sensors communicate with the flight controller using a microcontroller. A teensy LC is used for this purpose. Unlike other peripherals, the flight controller doesn't understand the data being transferred from the teensy. This data has to be transferred as a Mablink message to the ground station map proxy. Mav proxy is used to decode the Mavlink messages, and these are displayed in Python.
The chosen concept for the device's structural arrangement was a composite shell attached to a separate aluminium chassis. The composite shell's purpose was to create a seal around the device to protect the internals from ingress, ballistics, and the assumed harsh environmental conditions of the crater, while the aluminium chassis would provide housing and structural support for the device components. However, we found that the mass estimations for this configuration greatly exceeded our specified mass limit of 2.5 kilograms. We were also informed that the environmental conditions that the device must endure might not be as harsh as initially feared. Thus, the full encapsulation that the composite shell offered was now less of a critical requirement. The structural arrangement was redesigned into a single, lighter structure, as shown in the exploded view here. The chassis would now be comprised of two composite panels acting as the base and top plates, connected via nylon-encased steel bolt couplings. Acrylic panels were used between the composite plates to provide the device internals with shielding from excessive dust or debris.
Now that the shell and chassis has become a single component, it became very important to maximise the mechanical properties of the chassis material by selecting a suitable composite and manufacturing it to a high standard. Based on last year's research, updated requirements, pre-preg availability and manufacturing demands, 913 E-glass, a glass fibre reinforced epoxy derivative, was chosen as the most suitable chassis material. The fabrication process began with cutting the plies to shape using a CNC laser cutter for precision. The layup utilises 90 degree, 0 degree and plus minus 45 degree plies so that the laminate is able to distribute different kinds of loads effectively. Its symmetrical layup ensures that no thermal distortion occurs once cured, and the picture in the bottom left illustrates half the layup of the 2 mm thick chassis panel. After debulking the laminate to reduce the risk of voidage, laminates of varying thicknesses were vacuum bagged and cured overnight in the university's autoclave. Once fabricated, the cutting plan shown here was produced and the material cut to size. This included 2 and 1.5 mm thick chassis plates, 1 and 0.5 mm thick top plates, and numerous 0.5 mm thick square panels designed to cover the chassis' triangular cutouts. Material test pieces were also machined so that flexural and impact toughness tests could be conducted in line with ASTM standards. Due to technical issues with the computer used to communicate with the university's composite CNC machine, the components shown in this engineering drawing were manufactured at Quinier-Dufour on their CNC milling machine.
Due to the ever-changing nature of Fuego's crater, predicting how the device would land was a challenge in itself. Therefore, FEA was conducted for a couple of theoretical worst-case scenarios upon its impact. The first scenario was to load it so it simulated the chassis undergoing a flexural test. This may occur if it landed directly onto a rock and all of the device's weight was acting through the front and back of the chassis. The second scenario was if the chassis is put under torsion. Given the awkward terrain it would encounter, this scenario is quite likely to happen, not only upon landing but also during its exploration of the crater. Both simulations show that the maximum stress in the chassis, especially around the stress concentrators such as holes in the corners, remain well below the maximum yield strength for the material.
3-point flexural testing was conducted for a range of thicknesses in order to estimate the magnitude of deflection that the top plate and the chassis plate is likely to experience under a given load. 2 force displacement characteristics have been obtained from experimental data for the 2 potential chassis thicknesses of 1.5 and 2 mm. The nonlinearity at high loads is explained by laminate slip over its pin supports, which somewhat distorted the results. However, the calculation of flexural modulus is still perfectly applicable considering a large proportion of the graph correctly demonstrates a linear relationship. The average flexural modulus obtained from both sets of data is 43 GPa. The results were consistent with each other to within 2%. This results in an estimated chassis deflection of 8 mm when opting for the 2 mm thick panel.
Deployment of the device is critical for the successful completion of its mission. It was deemed that a multi-rotor UAV would give the rover the greatest chance of actually making it to the crater. The flight lab have 2 multi-rotors up to the task, a Vulcan UAV and DJI M600, pictured here. The rover is light enough that it could be carried by either drone. Now for delivery methods. There's airdropping, either with or without a parachute, or winching. Multi-criteria design analysis was used for selecting the method, through which it was reasoned that we could save on complexity and mass by avoiding a winch or parachute at the cost of greater impact loading. Winching would also place the expensive UAV at increased risk due to a prolonged hover near the volcano, and a parachute would decrease the accuracy of an airdrop. The rover could be attached to the UAV as a slung load or by a rigid attachment, and again for simplicity and cost a slung load was favoured. So that leaves us with a deployment like this. In reality, the drone will be controlled semi-autonomously through the mission planner software Tanya mentioned. The drone will be deployed from the ground station on nearby Mount Akatanango, carries the rover as a slung load for 2 kilometres before dropping the payload off in a location deemed appropriate on the day. A cord, firmly attached to the drone at one end, is passed through a central hoop attached to the rover's top plate and then goes back to the drone where it is attached to a servo release mechanism. This means that after release, the drone will not have lots of long wires for its wheels to get tangled in, and the load is directed through the base plate by 4 columns as seen on the left here, adding no additional constraints to the top plate so that it can stay as light as possible. The servo release mechanism which attaches to the underside of the drone looks like this. A metal geared servo powered by the UAV's flight controller is held in place by a snap fit as well as some bolts. When the servo head rotates, an arm moves outwards through a slot which will push a loop at the end of the cord off the arm, releasing the payload. Simulink and MATLAB were used to model the drone's dynamics with a slung load, as illustrated here. A simple version of the movement control system for a UAV was implemented, and a key assumption of the model is that the rover will be hung from a drone which has been well tuned. The displacement time graph on the left here shows a typical response. You can see the drone moves to its destination smoothly, without overshooting, and that the rover swings like a pendulum beneath it for a while, but there's no apparent threat to safe flight. The sensitivity of the drone's motion to the changing chord length are shown here on the right. It was reasoned that anything under half a metre should be completely safe, as the disturbances seen were the least prolonged. The model supports the opinion expressed to me by the flight lab that no issues should be faced, as well as third-party footage of similar setups being tested. We had planned to physically test many aspects of the deployment system through field testing prior to departure to Guatemala, but unfortunately the COVID-19 pandemic has meant that this was not possible. So this is as far as we got.
After having completed the development of the robot, we were finally ready to put it through its paces. We started off with a simple bench test. Then we moved on to lab tests, so we could see how well it can tackle obstacles and odd terrain. Now that we've seen it walk, time for it to run. We took the device out for some field tests, using a first-person camera on the device streaming to VR headset to control it. Given that this would be the method used to control the device during its mission, ensuring it was drivable over a variety of terrains and obstacles was vital. Then we moved on to testing the device in this environment, the closest analogue we could find to a volcanic crater, while in and around the engineering building. Finally, all of this driving would be wasted if it couldn't survive its landing at the start of the mission, so we conducted a drop test, which it passed with flying colours.
Overall, we feel we were successful in delivering a fully functioning rover capable of being deployed at Fuego's crater by the 18th of March. The prototype device was fully equipped to offer all of the high-priority functionalities agreed with the client at the beginning of the year, while weighing slightly less than 2.5 kilograms. These functionalities include the acquisition of environmental data, ability to traverse volcanic terrain, deployable from a UAV, capable of two-way communication with the operator, ability to withstand impact loads when deployed, and the ability to transmit video feed. Due to early closure of the university due to COVID-19 outbreak, there were a few things we'd like to have done that we didn't get a chance to do. The troubleshooting of error in communication of sensors with the ground station could not be completed. Further testing of deployment and communication range to assess the performance of the complete device could not be finished. However, When comparing the final device to the original specification, the group and clients are all very pleased with the outcome and excited to see it in action.
As mentioned previously, this device was designed with an aim to provide the flight lab with a functioning device before the 23rd of March. In order to meet this strict timeline, compromises had to be made to ensure timely delivery. In the future, continued development of this device can be considered in sampling retrieval and structural protection. From previous research and modeling, it was concluded that a 3-finger adaptive gripper in conjunction with a selective compliance assembly robotic arm, also known as CARA, could be suitable for this. This research can be further developed considering the storage capabilities of the device. To accommodate a storage unit, changes in the chassis would have to be made. If the device is to collect a sample, it must first be retrievable. This could be achieved using either modifying the robot so that it can be easily picked from the hovering drone, or developing a drive chain capable of returning the full distance of the ground station. Apart from this, various changes can also be made to the current subsystems. Improvement in thermal performance of the chassis can be done to protect the electronics and increase their life. Locomotion mechanism can be further developed to provide damping of the suspension to reduce rebound and vibrations on the impact. Further, a torque drive system can be developed to adjust the power delivery of each wheel depending on the requirement. The electronics can be further incorporate active range-finding sensors to provide obstacle avoidance during the mission. The sensing and control could also require to be further developed to identify a sample and assist in collection.
Thank you so much for listening. We have all thoroughly enjoyed having such an exciting and challenging project. Whilst the current epidemic has postponed the original deployment date, we are all eagerly looking forward to hearing about how our device fares against fuego in future field testing in Guatemala. Thank you.